Hi, my name is Jesus.
I'm Derek,
We're in section 5 and we're team 10.
and we've been working on our final project, which is counting bacteria.
So first, we clear the workspace in the command window. For test 1, we call the image and put it inside an array. If the image is named differently, just input the name of the image inside the apostrophes. Then we convert the image we called into black and white with the im2bw function. As you can see, the bw now is a 2D array with ones and zeros. Tasks 2, 3, and 4 are all inside a while loop. There's an initial condition and the loop runs while the condition is true. Task 2 plots figure 1 showing the black and white image of the bacteria and titles it. Task 3 asks the user to isolate one bacteria by selecting 2 points, the upper left and lower right corner.
Next, in task 4, we are asked to plot the isolated bacterium in another image, and for that we use imcrop. Imcrop basically takes the box that was defined by the user in task 3. Then imshow will essentially paste this image into another figure. Here's an example of our program's output for a single bacteria image. Task 4 also asks us to check if the user actually picked a row and column range with only one bacterium in it. And for that, we use the input function and ask the question. They can answer yes or they can answer no. If they answer yes, the while loop will be exited out of, but if they answer no, as you can see here, check will equal no, and the while loop will continue with prompting the user to pick another row and column range. In task 5, we are asked to find the parameters of an ellipse that best approximates the shape of the bacterium. As you can see, we use the edge function for this. Then, we used imshow to plot the isolated bacterium in another figure. This is an example of our program's output after we used the edge function. As you can see, it's almost like an inverted image except for the white outline of the single bacterium. The first parameter that we needed to find was the center of the ellipse. We decided that the best way to go about this was to find the midpoint of the white pixels in the x direction and in the y direction. So we used the find function to find the row and column indices of all the white pixels. Then we used the combination of min and max to find the column index of the center and the row index of the center. All we did here was display the coordinates of the center. After finding the center of the ellipse, we went on to find the major axis length and the minor axis length. Since we already had the coordinates of the center and the white pixels around it, our idea was that we could find the distance between the center and each individual white pixel using the distance formula. We integrated this idea into a for loop that you see here, and by the end of it we had a row vector called dist with all the lengths inside of it. The major axis length then would be the maximum of all the distances, and the minor axis length would be the minimum of all the distances. Then, as you can see over here, we just displayed our major axis length and our minor axis length values. Now, the only parameter left that we had to find was the angle theta that the bacterium was tilted to. For this task, we pictured a unit circle with the major axis length being this line right here. However, in order to find the angle theta, we would need to use trig functions, and for that we would need the adjacent length and the opposite length. The opposite length we called y-diff, and the adjacent length we called x-diff. We then proceeded to imagine the bacterium on a so-called Cartesian coordinate system with its so-called origin at the center. Following this, we had a long if-else statement describing every single possible case for theta. Theta could either be 0, pi over 2, pi, 3 pi over 2, or it could be in the first quadrant, second quadrant, third quadrant, or fourth quadrant. Again, after all of this, we displayed the value of the angle theta. Lastly, we inputted the parameters that we just found into the function PDE ellip, and we plotted that into figure 2. That way, we could compare the single bacteria image with the best fit ellipse.
We were able to find the bacterial count and position with the region plots function. We found the centers of all the clusters of zeros in the BWB array, thus giving us the position of all the bacteria. To find the bacterial count, we just found the length of the array with the centroids.